Hello, for this worked example, we've got a space truss here. So we've got 4 joints, A, B, C, D, arranged in a tetrahedron, and each of those members is connected to one another. And we are asked to find the force in each of the members of the truss shown below. So we've got a total of 6 members here, and we need to specify whether each member is in tension or compression. So since we're finding everything, I'm going to go ahead and use the method of joints. And so I need to, the first step, which is kind of optional in method of joints, is to find the reaction forces. So this whole truss is supported by a ball and socket joint here, which ball and socket joint is kind of like your shoulder. It allows for rotation in any direction, but it doesn't allow for any sort of motion. So I'd have a reaction force in the X, Y, and Z at point A. And these short links here, just indicated by a little line, prevent motion in one particular direction. So at point B, I'm just going to have a reaction force in the Y direction lining up with this link here. And at C, I'm going to have a reaction force lining up with X and Y, but no reaction force in the Z for point C. So I'm actually going to skip all of that. I'm going to jump straight into looking at the joints and see if I can solve it that way. So I'm going to start at point D, and you want to start always at a point where you have, with method joints, no more than 3 unknowns. So I'm going to have an unknown from AD, an unknown from CD, and an unknown from BD. So I've got 3 unknowns, 1 known force acting there. I should be able to solve for those 3 unknowns. Well, let's draw our free body diagram of point D. So at point D, here. So at point D, I'm going to have a couple different forces. So I've got the known force, this 600 Newton force, going down like this, and that is in the XZ plane, so it's kind of like this, and it's forward 30 degrees out of the plane. So it's got the angle there of 30 degrees out from there, and it's got a magnitude of 600 newtons. I've also got a force from each of these members that's connected to point D. So I'm going to have FBD, kind of like that. FCD is going straight back in the Y direction. And FAD kind of goes up like this. And I'm not going to draw in the directions on this. I'm going to go back and always use my diagram here to figure out the X, Y, and Z components of each of those. Because it does get a bit complicated with that. So I need to start drawing out my free body diagrams. So start with sum of forces in the Earth. I've got my free body diagrams. I need to start doing the equilibrium equations. So starting with sum of forces in the X, I need to look for which forces have a component in the X. Well, my load force has a component in the X. X is coming out of the board, and so does member BD comes out of the X direction a little bit. Member CD and member AD are in the YZ plane, so they don't have an X component there. So let's start with BD. And rather than using angles here, I'm going to be using the distance and hypotenuse version of all of this. So for that, which works a lot better with 3D problems. So for that, I look at how far am I going out in the, when I go from here to here, how far am I going in the X direction? I'm going to be going forward 2 meters, and I divide that by the total length of the member. So the total length of the member is the hypotenuse of a triangle. So I go forward 2 meters, divided by the length, the hypotenuse of this triangle, it's going to be the square root of 2 squared plus 3 squared. And I just use Pythagorean theorem there. And that coefficient is multiplied by my unknown force, FBD. Alright, so I've got that, and I also, remember, I've got my 600 Newton load force. And so that's at an angle. Since I know the angle, I'm going to go ahead and use sine or cosine, and the x component is going to be this bottom part here. So that would be the opposite side is going to be the sine. So it's going to be plus 600 times the sine of 30. And that whole thing is going to be equal to 0. That's my first equilibrium equation. Now let's go on to the y direction. So sum of forces in the y direction, and here I've got a little bit of everything acting on the member. So the only thing that's not acting in the y direction is my load force. My load force is entirely in the xz plane. But everything else, FBD, FCD, and FAD, all have a component in the y direction. And they're all going to be going to the left, which is negative for us. So let's start with FAD. And FAD, I'm going to again use the component hypotenuse version. So I'm going negative 3 meters this way in the x direction. My hypotenuse is going to be square root of 3 squared plus 1 squared. So it's going to be negative 3 over the square root of 3 squared plus 1 squared times FAD minus, let's look at FCD next. So FCD is just going directly in the y direction, so it's just negative minus FCD minus, and now I'm looking at FBD, so I'm going negative 3 in the y direction, and I'm going, my hypotenuse is the square root of 2 squared plus 3 squared. Same thing as I had up here. So minus 3 over the square root of 2 squared plus 3 squared times FBD. And that whole thing is equal to 0. Alright, last one is going to be sum of forces in the z direction. And so for sum of forces in the z direction, I've got my load force is going down in the z direction. These two, BD and CD, are both lying in the xy plane, so they have no z component. But FAD is going up. So FAD is going up. I go up by 1 meter in the z direction, and I divide that by the total length of the hypotenuse, which is the square root of 1 squared plus 3 squared. So 1 over the square root of 1 squared plus 3 squared times FAD. And then I subtract off the the vertical component, the z component of my load force. So minus 600, and it's going to be the cosine of 30. So minus 600 cosine of 30, and that whole thing is going to be equal to 0. Alright, so now I've got 3 equations, 3 unknowns. I just need to go ahead and solve it. So I'm going to start up here in my x equation. I've only got one unknown. I've got FBD, and if I solve for that, I find FBD is going to be equal to negative 600 sine of 30 divided by this number right here. So 2 over the square root of 2 squared plus 3 squared. That whole number. And if I do the math on that one, I should end up with a value for FBD of negative 540.83. Units are newtons. And because it's a negative number, I know that this member is in compression. I assumed tension originally, but the force is going the other direction. So I can do the same thing down here with FAD. I've only got one unknown. So FAD is going to be equal to positive 600 cosine 30 divided by this number right here. So 1 over the square root of 1 squared plus 3 squared. And that number, FAD, I'm going to get 1,643.17 newtons. All right, this is a positive number. A positive number is going to indicate tension in this number. Last one I need to solve for is FCD. So FCD is going to be equal to negative 3 over the square root of 3 squared plus 1 squared times my value for FAD, which is this number here. Minus 3 over square root of 2 squared plus 3 squared times the number for FBD, which is this number right here, so negative 540.83. And that whole thing will give me a value of negative 1,108.85. All right, and so that's a negative number. Units are newtons. Negative number indicates compression. So I'm going to fill in some of these numbers. Over here, I've got I had FAD, FCD, FBD. So those three numbers again. FBD was negative 540.83. This was compression. It was negative. FAD was 1,643.17. And this one was positive, so it was tension. And then finally FCD was 1,108.85. And since this was negative, it's also in compression. All right, so 3 down, 3 to go. Next thing I need to do is choose another point. So here on my diagram, I know this one, and this one. So my next joint, I can go A, C, or B, and I'm going to go to point B. So at point B, I've got 3 unknowns again. So I know FBD. I don't know these two members. I don't know the force in member AB. I don't know the force in member CB. And since I haven't solved for the reaction forces, I don't know the reaction force at B either. So I'm going to have 3 unknowns there. So if I draw a free body diagram of point B, I'm going to have the following forces. So I'm going to have the reaction force pointing in the y direction. We call it RBY. I've got a known force from FBD, and FBD again was in compression. It was in compression with a amount of 540.83 newtons. So we've got a force of about 540.83 going that way. I'm going to have a force from BC going straight back in the x direction, and a force up above that going kind of up to point A. This is going to be FAB, and that is going to be going in the XZ plane. Alright, so now that we've got that, let's look at some of our equilibrium equations. So sum of forces in the x, and again x is going in and out of the board. So sum of forces in the x, well, this force right here has a component in the x. FBC has a component in the x. FAB has a component in the x. So sum of forces in the x, it's going to be, draw an x, y, z. So the x, the magnitude of this is going to be, again, I'm using hypotenuse or component hypotenuse format. So 2 over the hypotenuse, because I'm going forward in the x. So it's 2 squared plus 3 squared times 540.83. And this whole thing replaces the sines and cosines we would be using in most of our 2D equations. So we've got that. We're going to have minus FBC. That's going straight back in the x direction. And FAB also has an x component. So that's going to be minus, and if we look back at our diagram, FAB is going back 2 meters in the x direction, and the hypotenuse is going to be the square root of 2 squared plus 1 squared for that triangle there. Alright, so there is my equilibrium equation for the x. In the y direction, I'm going to have my reaction force, so RBY. I'm going to have FAB and FBC aren't going to exert anything in the y direction. They both lie in the xz plane. But I do have this 540.83. That's got a y component. And the y component of that piece, it's going to the left, which is negative. That's going to be 3, which is the y component of the member, divided by a hypotenuse, or the length of member BD, which is 2 squared plus 3 squared. And I know FBD, which is 540.83. And that whole thing is equal to 0. And then finally, sum of forces in the z direction. So in the z direction, actually I have very little. So I've got FBD, FCD, those both lie in the xy plane. My reaction force is in the y direction only. So the only thing with a z component is member AB. And the magnitude of that is going to be how far I climb in the z direction. So 1 meter divided by my hypotenuse, square root of 1 squared plus 2 squared. So it's going to be 1 over my hypotenuse times FAB. And that's the only thing I have. And so the sum of forces in the z direction has to be equal to 0. Alright, so starting off with my z equation, I can quite easily see that FAB is simply equal to 0, which gets rid of it up here in my sum of forces in the x equation. So I can now solve the top equation for FBC. So FBC is just going to be equal to 2 over the square root of 2 squared plus 3 squared times 540.83. If I solve that out, I should end up with a force of 300 newtons. And so I've got FAB and FBC. This positive number is going to indicate a tension force. So 2 more forces down. FAB was equal to 0. And FBC, this one was equal to 300 newtons, and it was in tension. So 1 more to go. I've only got to find FAC, this last vertical number right here. And so to do that, we can go to either point A or point C. I'm going to go to point C since everything kind of lines up nicely with all of our axes. Alright, so at point C, let's draw our free body diagram. So we've got point C, I've got FAC, it's my unknown, it's going straight up. I've got the force in CD, so the force in CD was compression. It was 1108.83. I've also got the reaction force from that short number, so this little short link right there is going to cause a reaction, we call RCY. Alright, so in the X direction, I've got tension in FBC. So that tension in FBC, we just solved for it, was 300 newtons. And my reaction force, which I'm going to put pushing, I'm going to call RCX. Alright, so that's all the forces acting at point C. And I'm going to jump straight to, I've got, X is going in and out of the board, Y is left and right, Z is up and down. So I know FAC is in the Z direction, so I'm going to look at that one first. So sum of forces in the Z direction is just FAC. And none of these other forces, they're all in the XY plane, so none of them have a Z component. So FAC is simply equal to 0. And that is our last force in the member. Alright, so I bring this back over here. This is 0, and I've found the forces in each of those members. So I've got two zero force members, FAB and FAC, this one and this one here, two vertical members kind of on this side, and everything else is doing work. It's either got tension or compression in it. So with that, we've solved our problem. Thank you for watching, and I hope to see you again.